In light, we have different topics to discuss. Reflection is the change in direction of a wave between two different media, so that the angle of incidence is equal to the angle of reflection. Refraction is similar to reflection, except that refraction is the change in direction of a wave of light due to entering a different medium. The change in direction is due to the change in speed. A line drawn perpendicular to a medium is called the normal line when a wave of light leaves a denser media, such as water, and enters the air. The light wave will move faster. The wave of light will become further away to the line of normalcy, and opposite, the light going from the air into the water will result in the light wave getting closer to the line of normalcy. That's because as the light enters a more dense substance, it moves slower and it changes direction. The next one is dispersion. Dispersion is when light is separated from each other due to frequency. The most common example is rainbows. White light passes through the droplets, which are separated into Roy G. Biv, which is red, orange, yellow, green, blue, indigo, violet. Diffraction is the bending of light around an object. An example would be the shadow of an object. The edges are not fine lines because certain frequencies bend differently, resulting in rough shadow edges. Our next topic is polarization. Polarized light, the electric field oscillates in only one direction. Polarized lenses are essentially lenses with light filters. It can be compared to a picket fence and a rope, and you can vibrate the rope in any direction, but when you pass it through the picket fence, the vibration is in one direction. So essentially, it's a light filter on a lens that only lets light that's vibrating in one direction pass through. And our next one is interference. Light can have constructive interference and deconstructive interference. Deconstructive interference is when two or more coherent waves are superimposed. The two different light waves are in opposite motions. When the two waves of light move in unison, then they are constructive and amplify each other. And that would be constructive interference. And in the next part, we'll be talking about the what color or what a cyan costume appear under certain lights. Cyan pigment, which we've studied in class. A red light would appear black because it is totally absorbed by the pigment. Since the only light incoming is red, it is not reflected into the viewer's eyes and absorbed. Green light would appear green on the cyan costume because the only frequency of light interacting with the pigment is green, and since no blue frequency, is with the green, the pigment reflects only the green frequency. It's important to know that that cyan, magenta, and yellow pigments depend on both of their primary colors before being reflected to appear as the colored pigment. So, like yellow would be red and green, magenta would be blue and red, and cyan would be blue and green. And I'm going to have to make some more. Sorry about that, I had to make more room on my memory card. Anyways, where was I? I think I was on blue light. But, blue light would appear blue on the cyan costume, because it's similar to the green explanation. Cyan light, which is the combination of blue and green frequency light, would appear cyan on the pigmented costume because it's reflecting the appropriate light into the viewer's eyes. Magenta light would appear blue on the cyan costume because magenta light is the combination of blue and red light. The red light is absorbed by the pigment, and the blue is reflected into the viewer's eyes. yellow light would appear green because yellow light is red and green light combined, and red is absorbed, leaving green to be reflected in the viewer's eyes. And that's what our Halloween costume cyan pigment would look like. In the next segment, I will show you I'll attempt to show my ray diagram for my project. Thank you. Here I have my ray diagram. 1 over the distance of the object plus 1 over the image distance equals 1 over the focal length. My focal length is 35 millimeters. And so I have over here 1 over 15 millimeters plus 1 over my image distance is equal to 1 over my 35 millimeter focal length, which I rearrange that, and I get 1 over the image distance is equal to 1 over 35 millimeters minus 1 over 15 millimeters, which up here in a calculator I did 35 raised to the negative first minus 15 raised to the negative first, which is equal to negative 0.038095231, which then I take the answer and raise it to negative 1, and I get negative 26.25 for the image distance, which right here we have if the image distance is greater than 0, it's on the right side, which is defined as image the same side as the object. So in this case, it would be on both object and the image would be on the left side of the ray diagram, but that's not the case. I have a negative image distance, which if the image distance is less than 0, it's on the wrong side, which is image is opposite side as the object. And that's what I got from my project.